So let's begin with plastic deformation. There are a handful of slides regarding plastic deformation, and by the end of this video, and also considering that you've already watched the elastic deformation, then you will have fundamentals necessary to understand general mechanical behavior of materials. So by the end of this course, you will be able to explain most of the mechanical phenomenon happening within the materials, and it will qualify you for some jobs that are dealing with mechanical property of material. Having said that, this only gives you the platform. So you need to take these topics that we discussed and dive a little bit deeper to become an expert, to become really knowledgeable about them. But regarding the fundamentals and basics, these two videos will give you whatever you need to understand any kind of complex problem and to be able to dive in further, right? So plastic deformation, permanent deformation in materials, which is 180 degrees different than elastic deformation, which was reversible. So plastic deformation, especially in metals, has to do with shaping and bending pieces of materials permanently. We are shaping them. So if you remember elastic deformation, in the elastic region, we had a linear relationship between stress here and strain here. That was all our linear relationship. And this is the region, this triangle is the region for elastic deformation. Plastic deformation starts where elastic deformation ends. So when this linear relationship between stress and strain breaks down, then that's the beginning of plastic deformation. So in here, we have this linear line, and here, this linear relationship breaks. And that's where the plastic deformation starts. The non-linear region between stress and strain starts. So it's good to note that this linear relationship that we had in the elastic region no longer applies, obviously. So this was the elastic, and we are now entering the plastic region. I make the stress strain curve a little bit larger, and we have these lines already drawn because we want to divide the plastic region into different subregions and also talk about their stress and strain and the behavior of material related to that. So what we have in the beginning, in this point, the 0 point, what we have here is an unloaded material. It's a material that is not yet loaded, and it could look like that as a tensile specimen that we want to clamp onto a machine and start pulling. So that would look like that. And then we start pulling. So we first go up this linear relationship and until this point, that we have elastic deformation. Before this point, if you unload, it will go back to its original length. It will go back, set along this line, back to its original length. But once we are here, then we are entering plastic deformation. This point that marks the transition between elastic deformation to plastic deformation, we call yield strength or yield stress. So this point, we call it yield strength, and strength has something to do with the stress that your material can endure, right? Therefore, on the stress side, we have yield stress, right? In here, at this point. And then on the strain side of this, for this yield strength, we project it down, and that will be our yield strain here. It tells you, what does it tell you? It tells you that if you stretch, like yield strain, what does it say? What does it tell us? Yield strain tells us if you stretch, because strain is normalized displacement, right? It's like displacement. It tells you that if you stretch your material up to this much, like as much as the yield strength, If you go beyond that, then your deformation is no longer reversible. That's your yield strength. So if you stretch it this much, it will not go back. Yield stress also says if you apply this amount of load, this amount of stress, if you apply on the sample, so this is the stress that we are applying, right? This is our load because we are doing a tensile test, so we are pulling, and then that will be your cross-sectional area, and therefore F over your cross-sectional area equals your stress. So it says if you apply this amount of stress on your material and beyond, then you will stretch your material enough for it to enter the plastic deformation for it to be non-reversible. So that's your yield stress and yield strain. And this point also, which is corresponding to a stress, we call also yield strength, which is the beginning of plastic deformation. It means that you have stretched the helical spring in between the atoms so much that they cannot stretch anymore. So the bondings break. That's the beginning of plastic deformation, initiation of plastic deformation. When you stretch the helical spring between the atoms so much that they cannot endure it anymore, they'll break. The beginning of plastic deformation, yield, stress, and strain. When you enter plastic deformation, as we said, it's no longer reversible. So that's how the strength is changing. Yes, the strength of your material. It shows that it's increasing. So after entering plastic deformation, it will go maybe a little bit on the flat line, and then it starts to increase. And then we get to the top of the stress strain curve. The highest point on the stress strain curve, we call ultimate strength. So ultimate strength is the highest point on the stress strain curve, and it's certainly higher than your yield strength. So this is your yield strength, beginning of the plastic deformation. Ultimate strength is the highest point on the stress and strain curve, and its stress and strain correspondence are like, if you're here, then ultimate tensile stress will be here. That's your corresponding stress. And ultimate tensile strain, if you drop it down, will be here. That's your corresponding strain to the ultimate point. So in the ultimate point, you have a strain, and then also you have a stress. It again tells you that if you apply this amount of strain on your sample when you're pulling, if it's exceeding or at this point, you're at the highest point in your stress and strain curve or the highest strength of your material. It shows that when you enter the plastic deformation and you pull even more, your material, that's stress is an indication the strength of your material, right? It shows that the strength of your material is increasing up to the maximum point, which is the ultimate strength. So in another world, after beginning the plastic deformation, your material, it's starting to become stronger, and stronger as you apply more and more deformation, up to a certain point that we call ultimate strength. After that, another phenomenon happens that we call necking. So necking is exactly like my neck that is not as wide as my head and my shoulder. So you get this thinning effect that also you can see in this image. We have a thinning effect that the cross-section of your specimen will begin to thin and narrow down. So it's going to get smaller and smaller. Therefore, your material is becoming the smaller cross section is a tolerating load. So and defects will start to grow and the cracks will start to grow. Therefore, your material on this engineering curve will become, as it shows, weaker until it undergoes fracture. So necking the ultimate strength on this curve shows also the beginning of necking. That's where, from this point on, necking starts. And it becomes worse and worse and worse until it narrows down so much that your material cannot keep up with the load, and then it breaks. So necking, the initiation of necking is where your material becomes weaker and weaker. So we have two significant regions where the strength is increasing and where the strength is decreasing. When the stress is increasing, or your material becomes stronger as you apply more plastic deformation, we call it strain hardening, because you're applying strain and your material becomes harder and stronger. So we call it strain hardening. And after that, after ultimate point, we call it necking until fracture. So this is up to this point, the beginning of plastic deformation, the ultimate point in plastic deformation. Before that, we have strain hardening. Another word for strain hardening is also work hardening. So we have either strain hardening or work hardening before the ultimate point, and after the ultimate point, we have necking and continuous weakening of our material. So the cross section, it narrows down so much that it breaks down, as you can see on the image, on the right image, on, let's say, this image, that it breaks down. Okay, I make it a little bit cleaner here. All right. Now we want to talk about some more concepts. We have a concept called ductility, and the ductility has to do with the amount of deformation your material can take before it breaks. So it tells you if you're bending a metal bar, how much you can bend it before you break it. Now compare it to a glass bar. How much you can bend it? Pretty much nothing, right? If you attempt to bend it, you will break it. So a glass bar is not ductile at all. But a metal bar, you can apply a lot of plastic deformation, permanent deformation, before you even break it. And it might not even break when the legs are touching, right? When you try to bend it. So ductility is a measure of how much strain you can apply to your material before you break it. Therefore, if your material is really ductile, you can apply a lot of strain. Strain is a lot. And if your material is brittle, you don't have so much strain until fracture. Now, if you look at the slide, where is the fracture point? It's here. Strain at fracture is here. This is strain fracture. And this is how much from here to here. This is how much strain you apply on the material before it breaks. That's a measure of your ductility. Now, if you have another a curve for another material, let's say something like that it ends up here, okay? Then the corresponding strain at fracture will be somewhere here. Therefore, your deformation will be from here to here, and it's smaller than strain to fracture for this material. Therefore, you can say this material with this amount of strain at fracture is more ductile than this material with this amount of strain at fracture. That's a measure of ductility. So that's a definition of ductility. Now we have another concept that is called toughness, which is different than strength. Strength, as we said, has to do with stress. So when you say yield strength, it means the stress at the yield point. So yield strength means stress at the yield point. Ultimate strength means stress at the ultimate tensile stress point. So that's your UTS. So strength has to do with stress. Toughness has to do with stress and strain, has to do with work, with the amount of energy that your material can take before it breaks, or the amount of work that can be done to your material and work is a combination of stress and strain. The amount of work that can be done on your material before you break it. That's called toughness. And toughness, when you want to quantify it and measure it in stress and strain curves, is the area under the curve. That's toughness, because it's a measure of both strength and stress and strain. So area under the curve. So it's, for example, for this small one, when you drop it down here, this is until fracture, the area under the curve everywhere. That's the total amount of work that you need to do on your material to break it, and that's called toughness, the area under the curve. As you can imagine, for this material with this stress strain curve, the area under the curve is much larger, right? Therefore, the material with the blue line is much tougher than the material with the black line, than this material, right? So that's also toughness. So we discussed toughness, we discussed ductility, we discussed necking, and we also talked a little bit about strain hardening or work hardening, which is effectively, it means that your material becomes stronger as you deform it. So when you have a metal bar, if you bend the metal bar, on the bending area that deformation has happened, your material has become stronger. That part that is bent is stronger than the unbent area. That's what it means. And for every crystalline metal, we have this scenario that it becomes stronger, and we call it either strain hardening or work hardening. But we need to understand, as material engineers and as a part of mechanical engineering, why we have this strain hardening. What is happening? And that's the key to understand any deformation within metal-based materials. So it could be a metal, it could be an alloy, it could be a metal-based composite. But what is happening here in strain hardening would define most of the deformation phenomenon within the metal-based material. So if you understand this, you can apply it to many things. My students can testify for that, because once you understand this, they know, and they now can, most of them, explain the mechanical behavior of alloys, of composites, just by understanding these basic concepts in elastic and plastic deformation, especially this. So we want to understand why our material becomes stronger from the yield point, the beginning of plastic deformation, to the ultimate strength. To understand this, I'll resurrect a simple concept in material engineering, and that is crystalline material and amorphous material. Just quickly, your material can either be crystalline or amorphous. Within your material, you have these atoms next to each other. If the atoms have a long range order, they are really ordered next to each other within a long range, we call this material crystalline. If you have a short range localized order, which is not really applied throughout the material, then we call that material, that disordered structure, amorphous. So also, if you look at the image on the right, these chaotic, disordered red lines could be seen as amorphous, and the blue ordered regions could be seen as crystalline regions. Okay, so that's the difference between crystalline and amorphous. Now, within crystalline materials that we have order, now the image on the left with the cubes, the order can be arranged in different ways. So, sometimes it's arranged in this way. So these are the atoms, the black ones, and these are the bondings with them. Again, the helical spring. So sometimes they can be arranged in this or in this way, which we call body-centered cubic, or in this way, which we call face-centered cubic. Naming, just know different arrangements. But now that you have these arrangements of crystalline material, so these are crystal structures with different arrangements of atoms. Now, within these planes of atoms, within this ordered arrangement, sometimes So this is really ordered, right? This is a crystalline material with a certain arrangement of these materials. And then you have order, right? You can see order here. So these planes of atoms are right order perfectly next to each other, except for one. So as you can see, we have a line here. We have say a plane of atoms here, another plane of atoms nicely lined up here, another one really continuous here. This one is also another one. Plane of atoms nicely lined up to the end, except for one, in a crystalline and ordered material. That's important. So in an ordered material, you can identify tiny disorders. Now you can see we have an extra half plane in here with this symbol, with this notation that you see over here. So this extra half plane we call dislocation. This is an extra half plane that shouldn't be there, because if it was not there, then you had perfect crystal, perfect order. Now you have an extra half plane, which is not a complete also plane, that is there and is applying a little bit of deformation to the whole crystal, right? You see the top part is a little bit thicker than the bottom part, and that's that half plane, because we want to squeeze that in, it applies some strains and deformation to the crystal. So this dislocation, these extra half planes within the crystalline materials, and they are scattered throughout the material, and they are there thermodynamically stable in all crystalline materials, these half planes that we call dislocations. These dislocations are responsible for the increase in strength. These dislocations are responsible for this phenomenon that the strength is increasing and increasing and increasing until the necking point. So in the beginning, at the initiation point of plastic deformation, these dislocations, these half planes will start to move. Okay. So these half planes will start to move either say in this direction or in this direction. They start to move when you enter plastic deformation. Therefore, dislocations has no role to play in elastic region. Elastic region is only about the helical spring. In plastic region, however, when this bonding cannot take the tension anymore and it breaks down, then these half planes will start to move. They will be mobilized. But if they are mobilized, why the strength is increasing? If they're mobilized, either the strength should go flat, like that, like almost flat, like here, or even dropping, because after the bondings are breaking, then these dislocations are just mobile. They're moving throughout the crystal, throughout the material. So either the strength should go flat or even dropping down. Why is it going up? The reason is these half planes, when they start to move, just like a traffic jam, just like a very crowded street full of people, they start to collide and bump into each other and slow each other down and pin each other down. Okay. So when they are bumping to each other and they are slowing each other, then they cannot move as freely as before, like the beginning of this region. So they start to move at first here. They start to move, and that's all fine. But at some point, when so much of them begin to move, they start to collide and slow each other down. So when this huge amount of, let's say, people are slowing each other down, then if you want to push them from the back through a door or something, then you need more force. You need to apply more pressure, more force to push them forward. The same applies to these dislocations. So once they are colliding and bumping into each other, it takes more force and stress to move them even further. Why we want to move them? Because we are applying deformation. We are applying strain in this direction. But to be able to apply strain in this direction, you need to apply more stress to move them because now they are bumping into each other. And therefore, the strength of your material is increasing. That is the mechanism behind strain hardening or work hardening. And once you get it, you can apply it to all kinds of, almost all, uh, I think it's safe to say most of the plastic deformations of metal-based materials, because I was hesitating to say all or almost all, because slip and dislocations, like in this complete form, are not only responsible for plastic deformation. We have another mechanism of plastic deformation, which is called twinning, which has to do with partial dislocation. So dislocations are not this half line like perfect. They are partial dislocations playing a role in twinning. So usually for at the beginning of plastic deformation, the yield point, materials have two choices: either do the plastic deformation through a movement of these complete dislocations, which we call slip mechanism. That's how it's written. We call slip mechanism. That has to do with movement of these complete half planes, mobilizing them. And another a mechanism which is called twinning, just like a twin. It's called twinning, and twinning has to do with the movement of partial dislocation, which is slightly different. But metals have these two routes. Sometimes they take one or another, or sometimes they take both. So that's about plastic deformation and movement of dislocations within the plastic region, which is really important. To close this video, I have two nice videos of dislocations, these half planes under microscope actually moving through the material when the material is under load, and that's this slide. So let's first look at the image on the left. These lines are dislocation lines. And this material is under load. Look how the dislocation lines are moving. These are extra half planes. And because these extra half planes are moving, we know that the material is in the plastic region, not elastic region. In elastic region, they won't move. And here, next one. Look, they are now colliding also. You can see they are kind of bumping. Some of them are bumping into each other and colliding with each other. And that's the mechanism behind stress hardening or work hardening. That's how materials go through plastic deformation, and that's how material becomes stronger. So if you want to make a material stronger in the plastic region, what do? You try to slow down and pin down these dislocations with using any mechanism. If you can achieve that somehow you pin down these dislocations, you make your metal immensely stronger. That's the mechanism of behind the strength of materials in the plastic region. For elastic region, if you want your material to resist um, elastic deformations harder, because it has to do with atomic bonding, then you need to think about the bonding between the atoms, how strong they are and how mobile they are. So those are two different stories. That's it, all about plastic deformation. I hope you liked it. I see you next time. Bye.